So this lesson is pretty exciting because we're going to apply our skill set of factoring polynomials. Now that we're great at factoring, you did so much practice in the previous homework sheet, let's make use of that skill and try to solve polynomial equations. And if you're able to solve polynomial equations, you'll be able to answer a bunch of different word problems, just like you did in grade 9 with the linear equations and grade 10 with the quadratic equations. So let's take a look at our first example. Solve the equation x cubed minus x squared minus 2x equals 0. So just like we said in grade 10, we really want to factor the left side of this equation. It's set equal to 0, beautiful, but we really want to factor the left side. Why do you want to factor the left side? I'll say in a second, but let's just fully factor. Common factor x, this is a simple trinomial, always fully factor. And then what multiplies a negative 2 and adds a negative 1? Negative 2 and positive 1. So now it's fully factored. Why do you want to fully factor? Because now you can apply the zero product property. Okay, when is the left side equal to 0? Well, the left side is equal to 0 when any of these three factors is equal to 0. Because if one of the factors is 0, 0 times anything is 0. That's the zero product property. Alright, so when is x 0? When x is 0. When is x minus 2 0? When x equals 2. When is x plus 1 equals 0? When x is negative 1. So that's when the left side is equal to 0. When any of these factors is equal to 0. Okay? Or in fact, more than one of the factors. But there's no value of x that makes more than one of these factors equal to 0. So that's why we factor. Okay, just to remind you. I could not have told you that, for example, 2 is equal to 0 at the very beginning when it's not in factor form. I guess I could have told you, but that would have been a guess. Okay, it's not obvious that 2 makes the left side equal to 0. Alright, now maybe it is obvious in this case because the numbers are pretty straightforward, but you know what? If you look at example 2, can you tell me what's equal to 0 here? What makes the left side equal 0? Can you tell me the three solutions that make the left side equal 0? You might get one of those numbers, okay? In fact, you're going to have to guess once. So you might guess one of them, but finding the other values will be a little challenging, okay? So you may be able to guess the solutions equation, but our goal in this course is not to guess all the solutions to our polynomial equation. Can you do it? Yes. But our goal is to solve it systematically. Okay, we have a technique which is making use of factor theorem to factor the cubic. So let f of x equal 2x cubed plus 3x squared minus 11x minus 6. So f of what is going to give me 0? Because I really want to find one of those factors. I see 2 and 3, that's 5 and 6. So negative 1. Let's see if negative 1 works. No, negative 1 doesn't work, nor does 1 work. So you know what? I see that 2 actually works out beautifully. 2 works out. So since f of 2 is equal to 0, therefore x minus 2 is a factor of f of x. Remember, you want to factor because you can apply the zero product property. So let's see, x minus 2, what's that quadratic factor? You can use long division or synthetic division if you're not comfortable with this technique, but I highly recommend it. It's just such a huge time saver. So that's going to be 2x squared because I need to reach 2x cubed. Okay, this must be 2x squared. And what about the constant term? This must be plus 3, right? Negative 2 and 3 give me negative 6. Now, I need to make 3x squared. This is going to make me negative 4x squared, right? Negative 2 times 2 is negative 4. But I don't want negative 4. I want 7. I want 3. So this must be 7. Because this 7x times x will give me 7x squared minus 4x squared will give me the 3. Alright, so now factor this complex trinomial. So I'm going to put a 3 here and a 1 here because this will make 6. 6 and 1 will give me the 7. Beautiful. Now it's fully factored. I found my 3 linear factors. I am ready to tell you the solutions. 2 is a root because that's for my factor of x minus 2. Negative half is a root, okay? Because 2x plus 1 is a factor. And finally, negative 3 is a root because I have a factor of x plus 3. These 3 values can solve this equation. It will make left side equals right side. If you don't trust me or trust the math here, you can most definitely just sub it into left side and see if it's equal to 0. But the factor theorem says that it works out. I factored perfectly. So yeah, I really hope you appreciate why factoring is very useful. I'm pretty certain that no one would have told me that negative 1/2 was a solution to this equation just by staring at it. Okay, I'd be very impressed if someone told me that. Alright, so now let's look at f of x, 2x cubed plus 3x squared minus 11x minus x. And what are the x-intercepts of this graph? Wait a minute, this is what we just had up above, right? So guess what? The roots of this equation are going to be the same as the x-intercepts of this graph, because what's the first thing you do when you find x-intercepts? You let y equal 0, or in this case f of x equals 0, right? You let y equals 0, and guess what you have? You have that equation. You have the equation from 2a here, right? This is the first step you do when you are asked to find the x-intercepts. So the x-intercepts are negative 3, negative half, and 2. So there's another reason why we really want to factor. Factoring helps us find the x-intercepts for the graph of f of x or any other polynomial. So we're really trying to make use of this skill set of factoring. So in general, the x-intercepts of the graph of a polynomial function correspond to the real roots of the related polynomial equation. The real zeros of a polynomial function correspond to the x-intercepts of its graph. So this last sentence, the real zeros of a polynomial function corresponds to x-intercepts of its graph, we learned that in the previous unit or in the previous chapter. When you looked at the zeros and the orders, and that will tell you the behavior of the graph at that x-intercept. So we knew that already, but now we're just adding the first sentence. So when we talk about the real roots of a polynomial equation, that will also give us the x-intercepts. Okay, so question 3, they want me to find the x-intercepts of the graph. So what I'm going to do is I'm going to try to find the real roots to that corresponding polynomial function, which is 0 equals x cubed plus x squared minus 4x minus 4. Okay, and I always ask my students to do this question first because students always get so hung up on factor theorem, factor theorem, factor theorem. But I always advise them, before you try factor theorem and guess your zeros, the very first thing you should do is check if you can factor by grouping. Okay, so in this case you can most definitely factor by grouping. So always try to factor by grouping first, because it's a big time saver. There you go. See? No guessing, no need for using synthetic division, long division, all that stuff. Factor by grouping is a way to go. Saves you a lot of time, okay? So on the test, before you go crazy and then try to guess around, just check, can you factor by grouping? Because it's a good idea to do so if you can. Alright, so let's find the x-intercepts. Therefore, the x-intercepts are, let's see, plus minus 2 and negative 1. Okay, and if you want, what you can do in addition to stating the x-intercepts, you can also graph p of x. Okay, I really want to emphasize that, you know, you don't have to stop at just finding the x-intercepts. Now that you're able to factor polynomials, of greater than degree 2, you can really make use of that. In fact, and you're now able to graph polynomial functions that are factorable. So x cubed minus x squared equals 4x plus 6. I gave this question just to make sure that you remember you have to set it equal to 0. Okay, you have to make one side equal to 0, because otherwise you can't apply the zero product property. Okay, so set it equal to 0. And now I ask myself, can I factor by grouping? Unfortunately, I can't. Well, factor theorem is going to save the day. So I think 1 works out, right? Does 1 work? Ooh, let me check. One does not work out. 3 is our friend. Since f of 3 is equal to 0, therefore x minus 3 is a factor of f of x. Okay, so I'm going to write it over here. So it's x minus 3. Let's find the quadratic factor. So it's x squared, and that's going to be plus 2 over here. Now let's figure out the middle term. So that's negative 3x squared, but I don't want negative 3x squared. I want negative 1x squared. So that's me a plus 2 here, because negative 3 plus 2 will get me negative 1. Okay. So this quadratic factor, you'll realize you can't factor, because it's a simple trinomial, but you'll realize what multiplies to 2 and adds a 2. Well, not any integers that you can think of. So if that's the case, we have to use our best friend, or our old friend, quadratic formula. Now, x minus 3, easy peasy. X equals 3. So let's see, negative b plus or minus the square root of b squared minus 4ac all over 2a. Ooh, something interesting is happening here. 4 times 2 is 8, so that's negative 4. So I see square root of negative 4. So hopefully you remember from grade 10, when this happens, you have complex roots, or yeah, you can say imaginary roots, but the better term is complex roots, okay? But in this course, we're only interested in real roots, okay? So when we say solve, we're really solving for x such that x is a real number, okay? We're only interested in roots which are real numbers, so those are called real roots. So these are solutions to the cubic equation, but we're only interested in 3, okay? But on a test, you still have to show me your work. You still have to show the use of the quadratic formula, because you couldn't have told me that these roots from this quadratic factor were going to be complex, or they weren't going to be real. You have to do some work. For example, you can simplify it actually. You can just show me what the discriminant is equal to. You can show me the value of b squared minus 4ac. And once you see it's negative, you can say, oh, no real roots coming from this quadratic factor. Okay, but you have to show some work. You can't just assume that once you see a quadratic factor that's not factorable, and say that, oh, that's going to give me complex roots right away. Okay, so show me the work. Okay, now I see this. Beautiful. So there's only one real root, one real solution to example 4, which is 3. Okay, let's go. Let's try example 5 here. X cubed minus 3x plus 1. I like to give this question because students get really excited. They see a leading coefficient of 1. They see a constant term of 1. Like, yeah, the possible zeros are plus or minus 1. But I do this. I give this question on purpose because you'll see it's actually not as good as you think it is. So what's f of 1? That's pretty easy. F of 1 is negative 1, right? 1 plus 1 is 2, 2 minus 3 is negative 1. Well, that's not good. So you must be thinking, ooh, negative 1 is going to win or save the day for us. Wait a minute. F of negative 1 is 3. Well, That's not what we expected. So what is this saying? Okay, we tried all the possible zeros from the integral zero theorem. So what is this really saying? This is saying that this one's not factorable. Okay, the zeros are not integers. I don't know what they are. Well, we can find out. Okay, but the zeros are not integers, so we can't factor it. We need to use to find the zeros. You need to use different techniques. So you can use calculus to help you out. You can use graphing software. You can use some approximation techniques. There's a lot of different ways, but unfortunately, they're not going to be covered in this course. So if we were going to give you this question, what we would do is give you the graph of f of x equals x cubed minus 3x plus 1, and then you can solve graphically. Okay, we will not ask you to do this and to guess this because that would be rather silly. But now that I'm looking at this question, I am rather curious. So I'm just going to quickly find this. One second. Okay, so it's actually 1.532 approximately, negative 1.879, and approximately 0.347. So those are the roots for that equation. But like I said, we don't expect you to be able to do this question. So on the test, every time we ask you to solve an equation, it's definitely going to be factorable. If it's not factorable, we're not giving it to you, okay? Unless I give you a graphing calculator on the side. Okay, so let's move on to the next example. So for example 6, we have a box holds 2 CD-ROMs and the instruction manual for multimedia encyclopedia. The width of the box is 15 centimeters more than the height. The length of the box is 20 centimeters more than the height. The volume of the box is 2,500 cubic centimeters. Find the dimensions of the box. So before I do this question, I just want to mention that this question, I know algebraically the work involved is different than what you did in grade 9 and 10, but the idea is very similar. Okay, so in grade 9 you did lots of those linear problems. So for example, you solve linear equations. Johnny works at McDonald's. He makes $10 an hour. How long will it take till he makes $1,500? Okay, and you solve the linear equation. In grade 10, you did a lot of those projectile motion questions. You threw a ball in the air. When is the ball 10 meters high? And you did lots of those quadratic problems. And the idea is very, very similar here. Okay, so I'm going to draw a diagram. Okay, that will do. This width of the box is 15 more than the height. So I'm going to do h plus 15. And the length of the box is 20 more than the height. So h plus 20. And that's the height. Okay, and just like in grade 9, let h represent height of box in centimeters. Okay, so a nice let statement, beautiful, just like in grade 9 and 10. All right, so now we're going to build the equation. So the volume of the box is 2,500 cubic centimeters. So h times h plus 20 times h plus 15 is equal to 2,500. All right, so I always get students looking at this this line here, and they're always trying to look for some shortcut here. They're trying really hard to look for some shortcut, but unfortunately I have to break the bad news. You gotta do what you gotta do. You gotta expand the left side and then set it to equal to 0. And then you have to factor. Okay, so it is quite tedious, but it is what it is. Okay, so I'm gonna try to speed things up here. So that's h cubed. This is 20 plus 15 is 35, so it's 35 h squared, and 20 times 15 is 300, so it's 300h minus 2,500. Okay, let f of h equal h cubed plus 35h squared plus 300h minus 2500. And yes, that is a pretty big number, 2500. Yeah, but you know, a number is speaking to me. There's a number that is speaking to me. Absolutely. 5 was speaking to me. So f of 5, it actually works out. Oops. So take your time, always stay calm, okay? Now, if this was not factorable, then you must have done something wrong, okay? Always make sure your expansion is correct, because if the expansion is incorrect, which is a very common mistake by students, you have to go back and check your work. Okay, so if you're having a hard time factoring this, double check your expansion. But this one's pretty okay. It wasn't that bad. All right, so since f of 5 is 0, therefore we can say h minus 5 is a factor of f of h. All right, and if that's the case, guess what? We can solve, we're super duper close to solving this cubic equation, which will answer the word problem. So now find the quadratic factor. This is h squared here. That's gonna be 500, because negative 5 times 500 is negative 2500. Oops, positive, right? Negative positive will make me negative. Now, 35h squared. 35h squared. So this is going to be negative 5. So if I tack on 40, 40h squared minus 5h squared is 35h squared. Beautiful. Now let's factor this. So what multiplies to 500 and adds to 40? Let's see. Oh, I just realized this is not factorable. So, since it's not factorable, you know what? I have a feeling here. I'm going to check the discriminant of this expression here. B squared minus 4ac. Okay? Because I have a sneaky suspicion. Oh yeah, absolutely. 1600 minus 2000 is negative 400. So, since the discriminant is negative, therefore no real roots will come from this quadratic factor. Okay, the discriminant's negative, so no real roots is coming from this quadratic factor. So therefore h is equal to 5. That's it. There's only one real root. Okay, and only the real roots are meaningful for this question. So what are the dimensions of the box? Therefore the dimensions of the box is, let's see, h is 5, so 5 centimeters by, what about the other two dimensions, the length and the width? So 5 would make this 20, 5 plus 15 is 20, and 5 plus 20 is 25. So 20 centimeters by 25 centimeters. Boom. And you know what? Let's quickly check. 5 times 20 times 25. Beautiful, right? These three numbers have to have a product of 2500. If it wasn't, then you have to find your mistake. All right. Let's see. So this is a very, very common test question. So we have an open top box, which is constructed by cutting equal squares from the corners of a cardboard sheet that measures 14 centimeters by 8 centimeters. Determine the possible dimensions of the box, of the boxes if each has a volume of 80 cubic centimeters. So this actually bothers a lot of students. So I'm going to just draw a diagram because they're like, how do I make these boxes? So what you have to begin with is a cardboard piece of paper, or cardboard sheet, sorry. And what you're going to do is you're going to cut corners, cut squares from the corners of this sheet, okay? And then you'll have basically like a plus sign left over, and you fold them so you make these flaps. So if that's the case, any student of mine will tell you I'm not the most artistic person. All right. Okay, I'm gonna erase that. That's behind the box. Oh, that was a struggle. That was a struggle. Okay, that's a very ugly box, but you know what? It'll do for now. So this is our open top box. So that's how you make an open top box. You fold the flaps and then you tape them together and there's your box. So let's put some numbers in though. Okay, so let's say this is 14 and this is 8. And these are all squares that you're cutting. And let's say it's X. All right, so hopefully you realize that the height of this box is X. Okay, how big the squares are will control how big these flaps are, and the bigger the flaps are, the bigger the height of the greater the height of the box. Now these other two dimensions, the length and the width of the box, well, they're also controlled by how big these squares are. So hopefully you realize that this would be 8 minus 2x, and this would be 14 minus 2x. All right, so that was actually the hardest part to the question. Now we know that the volume of this box, this open top box, is 80 cubic centimeters. So bam. Oh, you could do a let statement too. Let x represent, let's say height of the box. Because you can say the dimension of the square that's being cut from the cardboard sheet as well. But you know what? I'll just say x represents the height of the box. That will do as well. Okay, so the first step, I'm actually not going to expand. I'm going to factor 2 and 2 from these two factors and make my life a lot easier. And I'm going to divide both sides by 4, which makes this 20. Just making these numbers smaller will help me a lot down the road. So this is going to be x squared. This is going to be minus 11x, because minus 7 minus 4 plus 28 minus 20 equals 0. And x cubed minus 11x squared plus 28x minus 20 equals 0. All right, let's factor this sucker. All right. Ooh. So I truly believe the hardest part to the question is done. Okay, the hardest part is drawing the diagram, or well, generating this model. Okay, generating this model. This line here is by far the hardest part to the question. Everything after is just testing your algebraic skill. Just don't mess up something really silly. Okay, so this is the hardest part to the question, and generating this algebraic model. Really, you have to have this picture in your mind. Okay, so you don't have to draw it out for me, but you know, you have to somehow have this visualized in your mind to generate this equation. Okay, so back to our game plan here, factor and then apply zero product property. So let's see, what is a good friend here? Two is our friend here. Okay, so 2 is our friend here. Let's see. X minus 2. And then x squared. This should be plus 10. And the middle term, this is going to be minus 2, but I want minus 11. So this is going to be minus 9x. What multiplies to 10 and adds a negative 9? Oh, nope, nothing I know of. So you can use the quadratic formula. Let me just check. Yep, these will give you real roots. I just checked because the discriminant is positive. So x equals 2, or let's say x equals quadratic formula. So 9 plus or minus 9 squared minus 4ac all over 2a Alright, so that was 7.7 or 1.30. Okay. Now there's a problem here that one of these we have to reject. Okay, one of them we have to reject. So hopefully you're going to say 7.7 we have to reject. Okay, it's inadmissible, or just say reject. Why do we have to reject it? Because take a look over here. How is it possible that I can have these squares to be having a dimension of 7 centimeters by 7 centimeters? That's not possible. There's only 8 centimeters to give me, right? How do I get 7 and 7? So, or 7.7, 7 and 7.7. So not possible. Those squares are way too big. I don't have enough cardboard to cut those squares out. 1.3 is fine, and 2 is fine, but 7.7 is definitely I cannot do. So we're gonna say reject because x has a greater than 0, and in fact the largest value of x that I can accept is 4, right? Actually, a number very close to 4 and less than 4. Okay, so any number between 0 and 4 I can accept. Anything greater than 4 equal to 4, no, I cannot do that because this dimension is 8 centimeters. Okay, so these squares have to have a dimension of less than 4 centimeters. All right, so therefore, okay, I ran out of room there, sorry. So therefore, what do we know? What are the boxes? The dimensions of the box is, let's see, 2 centimeter by, if x is 2, this would be 4 centimeters by 10 centimeters, or approximately, let's say 1.30 centimeters by, let's see, 1.3, 8 minus that, which is 5.4 centimeters by, that's 2.14 minus 2.6 is 11.4 centimeters. All right, approximately. Okay, so you know what? Let's check our answer here. 2 times 4 times 10, that's obviously 80. Perfect. Okay. I want that 80 cubic centimeters. Beautiful. What about this one? 1.3 times 5.4 times 11.4. So this one, it's going to be approximately 80 because these are all rounded figures. Yeah, 80.028. Good enough to me. You know what? Let's put 0.0 here. Just to stay consistent. All right. On the test, I'll tell you how many decimal places are rounded to, but I just felt like 2 was a good idea here. Okay, so the hardest part of the question was really generating the first equation, which I have to solve. And after that, the next common mistake would be right over here with the quadratic factor. Because for whatever reason, students just assume that the roots can be ignored here. Okay, just because it's not factorable, students just ignore the roots from that factor. And you most definitely cannot ignore the roots from that quadratic factor. As you can tell from this question, you know, you get a solution that is meaningful to this word problem. So do not neglect these quadratic factors. Is there more work to do? Absolutely. But you got to do it. Okay, so hopefully you really appreciate factoring polynomials, because it really opens doors and allows you to do so much more.